All right, welcome everyone. Today we're going to talk about the integral test. So this is a test that we can use to show whether a series is either convergent or divergent. So let's get into it. All right, so here's our test. Let's read through it. So let's suppose that we have a sequence a sub n, and it's a sequence such that a sub n is equal to some function f evaluated at n, where this function f is continuous, it's positive, and it's a decreasing function on this interval from 1 to infinity. So what does the integral test actually say? Well, it relates the convergence and divergence of the improper integral to the convergence or divergence of the series. So what does the test actually say? It says if the improper integral, so the integral from 1 to infinity of f of x dx is convergent, then our series, sigma a sub n, is convergent. And if our improper integral, that same improper integral, if that improper integral is divergent, well then the series, sigma a n, is divergent as well. So if our improper integral is convergent, our series is convergent. If our improper integral is divergent, then our series is divergent. Now, one thing to be careful of is that this integral test, it can be used to show both convergence and divergence, but it doesn't actually tell us what the sum is for our series. So just a little warning here. So we can use the integral test What can we use it for? Well, we can use it to determine the convergence and divergence of a series. But the one thing that it doesn't do is it doesn't tell us what the actual sum of our series is. So after going through the integral test, we'll be able to say whether our series is convergent, but we won't actually know what the sum is. So the integral test is really telling us the sum exists if our series is convergent, but it doesn't tell us what the sum actually is. So it's a common mistake, and we have it kind of the warning here. Once we go through the integral test, we'll be calculating this improper integral. And in general, the value of this improper integral does not equal the sum of our series. So it's going to be tempting, but that's not true. So in general, the sum of our series does not equal this improper integral. So just a warning there. So we can use the integral test to show convergence or divergence, but it doesn't give us the actual sum. All right. So as we're going through this, there's a few things we need to check before we actually can apply the integral test. So there's a few things we need to do before we actually compute the improper integral, and that's we have to really look at that function f. So function f needs to be continuous, it needs to be positive, and it needs to be decreasing. So positive or continuous, let's talk about that first one. There's no holes or jumps or breaks in our graph. And really, the big thing we're looking for here is, there's other cases, but one thing to look for is division by 0. So we're really looking for, there's other cases where we might have a discontinuity, but division by 0 is one of the more common ones. So if we have division by 0, well, then our function might be discontinuous. So that's something we need to look for. We also need to see if our function is positive. So again, that just means our function values are greater than 0. So we have positive output values. The graph of our function is above the x-axis. And the one that sometimes takes a little bit of work and that's not necessarily always obvious is that our function f is decreasing. So there's a couple ways to actually show this. We can show it either directly with using inequalities, or we can use derivatives and look at the sign of our first derivative. So you can do it either way. Sometimes one way might be a little bit easier or a little bit quicker, but you can do it either way. So how would we use inequalities? Well, function f is decreasing if, when we have two numbers, x1 and x2, and x1 is less than x2, then when we plug those numbers into our function, it reverses the inequality. So a decreasing function, if we take two numbers and one number is bigger than the other one, well, then when we plug them into the function, it reverses that inequality. So this is one way to show. Start with two numbers and then show that the function values satisfy this inequality. So we could use that definition. Another way, which is sometimes a little bit quicker, is to use derivatives. So we know that a function f is decreasing if the first derivative, f prime, is negative. So that's another way to do this. So we have to go through, before we actually compute the improper integral, we need to just kind of check, make sure these three conditions about our function are satisfied. All right. So why does the integral test work? And we're going to give kind of just a intuitive kind of sketch of why this proof, why the integral test is true. And we're going to kind of consider two cases: the case where our improper integral is convergent and the case where our improper integral is divergent. And so in the case where we have a convergent improper integral, what we can think of is we can think of our series, we can think of our series sigma from n equals 1 to infinity of a sub n. If we write this out, a1 plus a2 plus a3 and so on, we can think of each of these individual values of our sequence as really representing the height of a rectangle, or the area of one of those rectangles. So we could really think of, say, a sub 1, we could really think of that as a sub 1 times 1, where a1 is the height of a rectangle and 1 is the width. And so really we can think of, when we have a series, we can think of us adding up all these terms is really like we're trying to add up the area for a infinite amount of rectangles. And so in this first case, let's look at this case where our improper integral is convergent. We view our series in this case as rectangles, as representing the area of individual rectangles, each term that we're adding up. And so for instance, this first one, this first rectangle here, the area of this would be a1. It's the height times the width. And the area for the second rectangle is a2, and so on. And so the area of each of these rectangles is just given by the individual term in our series. So a1 is the area of the first rectangle, a2 is the area of the second rectangle, and so on. And so for a convergent improper integral like this, we're using the right endpoints to form our rectangles. So the right endpoint fits on the curve here for all of these rectangles. And those three conditions that we have to check. So our three conditions, that f is continuous, f is positive, and f is decreasing, guarantees that each of these right rectangles is below the curve. So that's why we need those three conditions on our function, because then when we look at all of these rectangles, all of the rectangles are below the curve. And so what happens here is we expect that the area of all rectangles, if we add up the area of all these rectangles, it should be less than or equal to, maybe excluding that first one, because we're going to be doing our improper integral from 1 to infinity of our function. So we want to start at x equals 1 here. So maybe excluding that first rectangle, but from then on, all of these rectangles here, the area of all of those rectangles should be less than or equal to the improper integral, which represents the total area under the curve. So if the total area under the curve, if the exact area under the curve is finite, well then the area for all those rectangles is finite. So it means the sum exists. So the sum of this series would exist. Now for a divergent case, it's the same idea, but now we're using left endpoint rectangles. So we're still viewing each term in our series as the area of a rectangle, but now we're kind of using the left endpoints. So when we look at this, our rectangles, the height of our rectangle is given by the left endpoint. And so again, A1, we're viewing A1 as representing, kind of, if we view it this way, the width of this rectangle is 1, the height is A1, and so the area of that first rectangle is equal to A1. Area for the second rectangle is A2. So the height is given by our function value evaluated at 2, and then that represents the height of this rectangle. And so again, those conditions on our function f really help ensure that these left rectangles, these left endpoint rectangles, they all fall above our curve. So you can see there's all this little pieces of these rectangles that lie above the curve. And again, it comes down to those three conditions. And so what's happening here is we expect the area of all of those rectangles added together. If we could add up all of those areas for each of these individual rectangles, add them all together, we would expect that to be greater than or equal to the total area, the exact area under the curve. Let's call it the exact area. And the exact area, if we get rid of those little sections that go above, well, the exact area would be, that's what our improper integral is measuring, from 1 to infinity. And so the area of all these rectangles, if we could add them all together, has to be bigger than the exact area for the area under the curve. And we know in this case, the improper integral is divergent. So if this improper integral is divergent, it means the exact area of the region under the curve is infinite, which means adding up all those rectangles, the area of all those rectangles, that has to be divergent as well. It has to be an infinite sum. So, choosing these rectangles like this, having this divergent improper integral that fits underneath them kind of forces the sum of all those rectangles to diverge as well. Whereas in the convergent case, if we fit all of the rectangles under the curve, the fact that our curve converges, the improper integral converges, it forces the area to be finite. So it forces our infinite series to have a finite sum. So this is kind of the intuitive idea of what we're doing with the integral test. But let's actually try it out. So let's actually start with example 1. And we're going to use the integral test here to show that the series is either convergent or divergent. And we're looking at the series from n equals 1 to infinity of 1 over n squared. And so there's a few things we have to do to kind of get started with our integral test. So the first thing is we have to define the function, f of x. And really, we just look at the term of our series here and just change the n to an x. So how we would normally do this is just say, we're going to look at the function 1 over x squared. So you can just replace the n's with x's. And so this is the function we're going to consider. So we have to go through and just check those 3 conditions to make sure this function actually satisfies those 3 conditions. So let's start. F is continuous. Let's check that. So why is this function continuous? Well, it's a rational function. And we're divided, the only place we divide by 0 is when x is equal to 0. So let's just say it's undefined at x equals 0. And that's okay, because we're starting with x values, we're starting at 1 and then going to infinity. So our interval here is from 1 to infinity. So f is continuous on that interval. So it's okay that we have a discontinuity at x equals 0 because that's not in our interval. All right, so that's the first thing. It's a continuous function because it's a rational function, which is only undefined at a place outside of our interval. F also needs to be positive. So this function is positive on the interval from 1 to infinity. And that's because if we look at it, the numerator, it's positive 1. X squared is always positive. So everything here is positive. So really not too much to show there. Everything is positive. Now the one that might take a little bit of work is decreasing. So we want to show that f is decreasing on the closed interval, on the interval closed at 1 up to infinity. I want to show it's a decreasing function. And we can do this using inequalities. So we could do it with derivatives as well. Let's just do the inequality argument here just to see what that looks like. So let's try it out. So we suppose we have 2 numbers, x1 and x2, and they're both just bigger than or equal to 1. So we have 2 separate numbers, x1, x2. They're both bigger than 1, and x2 is larger than x1. And what we're going to ultimately do is show that when we plug those values into the function, it reverses the inequality. So let's see what happens. So we start with x1 less than x2, and then we can square both sides of this equation, or this inequality. And so squaring, that preserves the inequality. So x1 squared is going to be less than x2 squared. And then once we do that, we can do the reciprocal of both sides. So 1 over x1 squared, 1 over x2 squared. And when we do the reciprocal actually reverses the inequality. So when we do the reciprocal of the left, that's going to make 1 over x1 squared. That's actually going to be the bigger term. And what's happening on the right, that's going to be the smaller term now. So what we've just shown is we've started off with 2 numbers, x1 and x2, where x2 was bigger. And with this sort of inequality argument, we've just shown that when we plug x1 into our function, that actually gives us the bigger number. So 1 over x1 squared is greater than 1 over x2 squared. And this is just our function value at x1. This is our function value at x2. So this shows decreasing. And again, that's because we could really think of this as f of x1 on the left is greater than f of x2. So this is kind of how the inequality argument works. So you just start off with two numbers, one bigger than the other, and then you try and reproduce your function and show that the inequality gets reversed. All right, so we have our three conditions here. We know that they're all satisfied, so that's good. So now we can actually go do the integral, apply the integral test. And so this is where we calculate the improper integral. So let's actually do that next. So we had our function, we stated our function, we showed those three conditions were satisfied. Now we're going to do the improper integral. So we're going to do the integral from 1 to infinity of our function, 1 over x squared. This is an improper integral. So we go through our standard procedure where we first rewrite this as a limit. So we're going to do the limit as b goes to infinity of the definite integral from 1 to b of our function. And we go through the process. So this is just a regular definite integral now. So just go through the usual procedure. Find the antiderivative. So the antiderivative of 1 over x squared is negative 1 over x. Kind of a power rule there. And we're going to evaluate that antiderivative from x equals 1 to x equals b. We still have to do the limit as b goes to infinity. Now we plug in. So we found our antiderivative. Now we evaluate. So we get the limit. We still haven't done the limit yet. And we get negative 1 over b plus 1 when we evaluate. So the top number goes in first. We get negative 1 over b. The lower number goes in second, so we get negative 1, and then we subtract like we normally do for a definite integral, so we have a double negative, so it becomes plus 1. All right, so we have our value here. Now we actually calculate the limit as b goes to infinity, and the fraction here is one of our c over infinity forms. So it goes to 0. So we end up with 0 plus 1, and that's actually us calculating the limit. So we've recognized that this is a c over infinity form, so that fraction goes to 0, and we're left with just that plus 1. So we get 1 as our improper integral. And so our improper integral is convergent. And so what that means for us is that our original series, sigma 1 over n squared, is convergent as well. So it's convergent by the integral test. And so just a little note here. Again, it's tempting because we get this nice numerical value here. It's tempting to say that the sum of our series is equal to that value, and that's not true. So our series, the sum of this series does not equal 1. So the only way we're actually using this numerical value here is it allows us to say that our improper integral is convergent. So because our improper integral is convergent, that means our series is convergent by the integral test, but this value is not the sum of our series. Now, this was an example where this is a p-series. So we already knew this. We could do this. And it turns out we can use the integral test to show that p-series result that we've seen before. So the integral test is how we actually kind of come up and show the convergence or divergence for all of these p-series. It's the integral test. All right. So just the kind of usual warning, well, tip here, I guess, disclaimer, is that we kind of start with the test written out in kind of the ideal setting, and then there's certain things we can relax a little bit. So if we go back to the original statement of our test, the index started with n equals 1. We can relax that. So we can start at other index values, and the integral test still applies. We can also relax those conditions on our function f a little bit as well. So, we originally said f had to be continuous, positive, and a decreasing function. Getting all excited. So we said f had to be continuous, positive, decreasing on that interval from 1 to infinity. Well, we can relax that a little bit. It just needs to eventually satisfy those three conditions. So what do we mean by the word eventually? Well, we can find some interval from n to infinity where it does actually satisfy those conditions on this interval. So there might be a few places sort of at the beginning where our function kind of misbehaves a little bit. But if we go far enough out, eventually from then on, it satisfies those three conditions. And so what we could look at instead is we could look at the convergence or divergence of, if necessary, of this improper integral, where instead of starting at n equals 1, we could just start at this other larger value if necessary. So we could start at, say, capital N. And as long as this improper integral converges or diverges, then we can say what happens to our series where we start with, instead of starting at n equals 1, we start at this larger number, capital N. So, we can kind of relax the starting index value here, and it's okay. So we could look at the convergence or divergence for this improper integral where we start at some other starting value, capital N, and that'll tell us what our series is doing if we start our series at capital N and go on. And the reason why this really works out is the convergence or divergence of a series doesn't really have anything to do with our first few terms. It has to do with what happens from a certain point going forward. So if we were to kind of look at a series, if we were to write out all the terms of a series, A1 plus A2 plus A3, and so on, up to A capital N minus 1 plus AN plus AN plus 1, and so on. That's a subscript there. So what's happening, what this tail of a series is saying, this little result is saying, is that if we look at the series where we sigma AN, where we start with index capital N, that series is convergent if and only if the entire series is convergent, starting with index 1. And the reason is because if we look at these first few terms here, these are just a finite number of terms that we're trying to add together. We can always add up a finite number of terms. So that's not where the issue is. The issue is what happens when this just keeps going. That's where the issue is. Potential issue is. So adding up the first few terms, we can always do that, no problem. Where the convergence, the question of convergence or divergence comes in, is what happens at the tail of our series here, the the part that goes on to, goes on forever. What happens there? That's where convergence or divergence gets interesting. The first few terms, we can always add those together. That's no problem. It's these ending ones that stretch on forever. That's where things get interesting. And so that's what this result says. So if we look at the series where we start at some other index capital N, that series is convergent if and only if the original series starting with index 1 is convergent. All right, so we can always kind of relax this starting index value a little bit, and also the conditions on our function. Let's try example 2. Let's look at example 2. Another integral test here. And first, let's decide on the function we're going to use. It's kind of the first step. So what is our function? So look at our general term here. Just replaced all the n's with x's. So we're going to use natural log x divided by x. Again, just replacing all of our n variables with x's. Then we have to go through and check those three conditions. So is it continuous? So it is continuous on the interval from 1 to infinity because, well, natural log is continuous, and the only place where we're dividing by, where we might have division by 0 is, again, when x is 0, and that's outside this interval. So check. This is satisfied. ln x is continuous, and we're not dividing by 0. Just to give a little bit of justification there. All right, so we know our function is continuous. That's good. What about positive? F is positive. Is it greater than 0? And this is where, not quite. So when x is 1, we actually get 0 here. So for our this positive requirement, we would actually have to go out to the next integer if we want to keep these as integer values, which kind of makes sense because we're talking about integer values for our sequence or our series here. So if we wanted to keep this as an integer, f is positive on the interval from 2 to infinity. But again, that's okay. So we can relax that condition. F doesn't have to be positive every single place. It has to be eventually positive, which we're seeing here. So natural log ends up being positive. X is a positive function for positive x values. And so we have a positive number divided by a positive number. The result is positive. The only time we run into a little bit of trouble there is when x is 1, because then our function value is 0. But that's okay. Just go a little bit further out, and then we don't run into that trouble anymore. All right, so that's satisfied. We also need to check, is f decreasing? So this one takes a little bit of work. So let's check and see if our function is decreasing, and this one we'll use derivative for. So let's try our derivative approach. So let's calculate f prime. What is the derivative of this? We have to use quotient rule. So let's work it out. And what would it be? Well, it'd be 1 over x times x minus natural log x divided by x squared, which ends up simplifying to 1 minus x squared, or 1 minus natural log x over x squared. Just using quotient rule here. And we want to figure out, where is this derivative negative? So we want to know, when is 1 minus the natural log of x over x squared? When is that less than 0? And really, this division by x squared X squared is a positive number, so that's not going to influence us in any way. So we really just need to figure out when is 1 minus the natural log of x? When is that less than 0? And if we keep going, add natural log x to both sides, we get 1 is less than ln x. We're trying to solve for x here in this inequality. And if we apply the exponential function to both sides, we get e raised to the 1 on the left, so just e. And then we get e raised to the natural log x on the right, and the e and the natural log cancel, and we're left with just x. So x is decreasing. Well, we're seeing that f prime is negative when x is greater than the number e. So what this means is f is decreasing on the interval. If we want to keep that as a integer value here, we need x to be greater than e. So let's go to the next integer, which is 3. So f is decreasing, and that's because our derivative here is negative when x is greater than e. So f is decreasing. It is decreasing, but again, it doesn't happen right at x equals 1. There's a little bit of a part of our interval here where our function might actually be increasing. That's okay, because eventually, once we hit x equals 3 and onward, eventually our function is decreasing. So we can proceed. So it eventually satisfies all 3 of these conditions, so we're good. All right. So let's actually go through and do the improper integral now. So we're going to do the integral from 1 to infinity of our function, which is natural log x over x dx. First step for an improper integral, rewrite it as a limit. So we're going to do the limit as b goes to infinity of 1 to b of our function. Now this is just a regular definite integral here, so we can just go through all of our integration techniques that we have. And so this isn't quite such an easy one as the one we saw last time in the example 1. We actually probably have to use a substitution rule here. So we want to find the antiderivative. Once we have the antiderivative, we'll plug in. And so to actually find this antiderivative, kind of leave it for you to work out the details, but you're actually going to do a u sub. So you'd let u equal natural log x, and then the differential conversion would be 1 over x. du would be 1 over x times dx. So you'd want to rewrite this fraction, probably to kind of see how the substitution would work. Try to separate this fraction. So write it as natural log x times 1 over x. And then you can kind of see how the substitution would work. So this is maybe some details for you to fill in. But in any case, when we do this, we end up with the antiderivative as being 1/2 natural log x squared. And then we're going to evaluate that from x equals 1 to x equals b. So we found our antiderivative. Took a little bit of work there, but we got it. Evaluate. So the top number goes in first. Still, we haven't done anything with the limit, but we're still writing it, going from step to step. Plug the top number in first. We get 1/2 natural log b squared. Plug the lower limit in and subtract. We get minus 1/2 natural log 1 squared. Natural log 1 is just 0, so this whole second piece here just ends up canceling out, ends up just being 0. And so we end up with just the limit of 1/2 natural log b squared as b goes to infinity. And we just need to know, what does the natural log function do as the term inside it, as b gets larger and larger? And the limit of natural log is infinity in this case. So the limit of this whole thing goes to infinity. gets larger and larger. And so what this means is because we did not get a finite number here, it means the improper integral diverges. And because our improper integral diverges, well, that means then our original series diverges as well. So we say our series is divergent by the integral test. So you want to get into the habit when we make one of these claims of first stating the result, so it's divergent, but then state which test we actually use to show it. So we actually use the integral test here. All right. So there's a little bit of work here with the integral test. We have to calculate the improper integral. There might be some work here actually getting the antiderivative. And then before we even get there, though, we have to decide on a function, and then we have to check these three conditions. And sometimes this decreasing condition takes a little bit of work, like we've seen. So going back to the statement of this test, the integral test, it's nice in that it can be used to show that a series is either convergent or divergent. One of the trickier things with it is there's a lot of conditions to show, and ultimately the function f, we have to be able to integrate it. So that's another kind of important thing here. So it might sound kind of silly to actually write this out, but it's worth mentioning because we've kind of developed a lot of integration techniques along the way. And, being able to actually integrate the function is not necessarily an easy task. And so that's a kind of a hidden thing here is once we've decided on our function f, yeah, it needs to satisfy these other conditions. But in order to calculate this improper integral, we need to be able to integrate it. We need to be able to find the antiderivative. And sometimes that can be a little bit complicated. So that's just another little thing to kind of consider here when we're going through all of the different tests that we're going to see and decide on which method to use. All right. So this is a good place to kind of leave off. The integral test, though, is nice because this improper integral, we're using it to show if our improper integral is convergent, then our series is convergent. If our improper integral is divergent, well, then our series is divergent, as long as all of these other conditions are satisfied. All right, so we're going to keep on. Next lesson, we're going to learn another test. And then the lesson after that, a test. So we're going to go through all these different tests for series. And the integral test is nice because it kind of gets us really started. As we saw in example 2 here, or example 1 here, we can use the integral test for all of our p-series. So if we wanted to go through and actually show our p-series, this is how we would do it. All right, so next time we're going to be talking about, well, another series test. So we'll see you then. Bye-bye.